Hello everybody and welcome back. So we've spent the last few lessons talking about Vex, sort of just doing a basic introduction on how to write code, how to write lines in Vex. Basically we've been learning grammar, okay? How to structure and write a sentence. And just the same with the Houdini expressions and HScript, there is a dictionary, okay? When you're wanting to slowly build up your vocabulary, it is totally worthwhile to have a dictionary at hand, okay? And then over time, you memorize whichever expressions you use the most, but you always want to have a list of what expressions are available because you're always going to be developing something new, something that you've never done before. You need different expressions. There's also new ones coming out all the time, so it's definitely worth using that. And that's what we're going to be talking about today, is how to find how to find the list of what the expressions are doing, what arguments it needs, what other options and overloaded functions there are. So if you pop open a help file, any help browser here or in one of the windows, and in the search bar you type Vex fun. Why? Because Vex is fun. So if you type Vex fun, you're going to see the Vex functions under the user guide. And if you go here, this is going to have everything you need. This is the one document that you really need to learn Vex. Sure, there are others. You'll see on the side here, there's a Vex language reference, and it teaches you about arrays and strings. There's learning like VOPs. There's a Vex cookbook, a few things. So it's definitely, if you're really interested in learning Vex and furthering your knowledge, definitely worth going through all of this. A lot of it is stuff we've already covered, or some of it is quite advanced as well. So just don't confuse yourself. But the main document you're going to want is this Vex functions list, because as long as you know how to structure a sentence in Vex, how to write a line, how to, then this is the dictionary, okay? This is the full list of what we can do inside of Vex, okay? So it's got a handy filter, so we can search for something. You just type the word point, and it's going to come up with everything that has the word point in the expression. So sometimes even when I'm looking for a particular function, something that I don't even know if it exists or not, like the centroid function, I say, okay, well, we do have a centroid function in HScript, so I'll come here and I'll look for centroid, and the only one is this fuzzy logic centroid. So okay, well, maybe centroid is not what I'm looking for, but if I type cent, then it gives me bounding box, like the point bounding box center or get b box center. So you can kind of guess what it may be called and actually find functions that you didn't know existed. Okay, so there's a filter for you. They're also listed under different categories, but alphabetically within that. So you can actually switch here to just sort by title, and then they will all be alphabetical, not in their groups, although generally this is going to be more useful. And then there's also some tags, so you can actually isolate different things you're looking how to do, maybe transforms, then it's going to isolate just that list. Okay. And then under each one, it's going to list a brief explanation of what it does, but then you can open up onto that page and it's going to give you much more detail on what it's going to do. Other examples, and then other related topics, links, and expressions. Okay, so very, very useful. I pretty much have this open the whole day while I'm working, because as you're typing, even just expressions that you already know, but you forget the order of the arguments, because sometimes there's the point for example, the point function in Vex does something very similar to what it does in HScript, except the number of arguments is different and the order is slightly different. So even that is confusing if you use it every day. So keep it open. And what I've done today, I've got a few examples open all of them are in this list, and I've just opened up the help card to all of these different functions, and I'm going to use these to explain how to read the help file. Now I know that might sound quite obvious, but it's not. There are certain sort of tricks, things that you need to look for in the help file, which are going to give you, I mean, the information's right there, they're giving you everything you need, and yet you'll sometimes miss certain things and struggle to use the function, or it won't work for you quite the way you'd expect unless you know what it's doing. So I've got normalize open. So if you guys want to follow along, I'm just going to run through these so you can open them up as well and see what's in the help card. Absolute, so the ABS, XYZ dist, which is kind of like a raycast function. So it's like the ray node. The XYZ dist does pretty much everything that the ray node does. Then point, which is actually going to take you to this page. It won't look like the others. It won't take you to the top of the page. It's actually going to jump down to this part of the reading attributes page. Okay, and then the access frame cop function. Okay, so these are not necessarily ones that you're going to use often. Well, okay, I haven't ever used this access frame, although I'm sure if you're using cops then you will, but some of these you do use quite often. But I didn't pull these up because they are common expressions, but rather as examples of how to read the help file. Okay, so I'm not saying you need to go and memorize each of these. It's more about an example of how to read it. Right, so let's have a look at normalize first, because I pulled this one up because it's quite simple. Essentially what you're looking at is the name of the expression, an explanation of what it does, and then this little section shows you essentially how to fill it in. It gives you the list of the arguments with the name of the expression, and it shows you the type that is returned by this function and the type of each argument as well. And this is very, very important. Okay, that right there and that right there, as well as the list of arguments, is vital to understanding how to use this function. Okay, so you know that this is going to be returning a vector. So if you say f at foo equals, and then you run a normalize function, well, you know, you're only going to be getting the x value of that vector that the normalize function is going to be returning. In the same way, if you feed it a float or an integer or a string instead of a vector here, then you're not going to get the right result. Either it's going to error, or if you feed it a float, I'm not even sure what it'll do. It might even default to taking the value that you feed it as x, and then y and z will be set to 0, or it may just totally error out and not do a single thing for you. So it's important to know what you need to feed it, and it's important to know what it's going to actually return. Okay, now when I say return, what it means is the vector, well, so the expression itself is going to give you a value. Okay, so that you store that inside of something, a variable or whatever. Okay, there's no sense in just running the normalize function on this vector, because the result of this function does not affect the original vector. Okay, I'm going to jump into Houdini here just to give an example of exactly what I mean. So if I create a vector, so I'm going to write this out so we can actually see it in our geometry spreadsheets. I'm going to say v at myvec1 equals, and then let's give it, let's say 1, 5, 3. Okay, so there's our vector myvec1. Okay. In fact, for simplification, I'm going to put it on in detail, so we're looking at only one. There's no point in doing it on every single point. So I'm going to go to detail view, and we're going to see here that it's got literally 1, 2, 3, okay, x, y, z. Right? Now, if I just say normalize, and I feed it that vector, so actually let's cast it. at myvec1. Okay. Now it's not complaining, nothing's broken, it is working, it's doing exactly what it's meant to do. But it is not writing data to this vector. What it is doing is returning a value. In other words, we give it some information, it does some calculation and returns a value that we can store as something else. So if I say v at myvec2 equals normalize, then the result of that normalization is stored in this new vector. Okay. Now it is possible to just write this over vec1, myvec1. So we've gone from what the vector used to be, and instead we're normalizing it. So we just overwrite it with the normalized version of itself. This is fine, you can do this. But you just need to be aware that you have to do this first bit. You have to actually take the resultant value of this and store it back in that value. If you just have this, it's not going to do anything. Okay, and that's what I mean by returning. And it is very important when doing coding to understand what your functions are returning. Okay. For example, if I go to access frame, right? The reason I popped this one up is because it says void. If you see it says void, what that means is that this function is not returning anything. So in your code, you would have the word access frame and you would just feed it a frame, an integer frame number, but you do not need to have a variable or an attribute where you're storing this information, because this is not going to give any information that can be stored. It is just going to go and perform a function. Okay, so that's the only reason I popped up this particular expression. You'll find that the majority of vex functions actually do return something, but a lot of them that kind of go and just perform a certain operation, something like this, instead of returning void, will return an integer, but the integer it returns is simply a 0 or 1 to say whether it was successful or not. Or sometimes it'll be a -1 if it failed and a 1 if it succeeded. So there are certain functions, even though that says it does return an integer, where you don't actually need to store that value in a variable unless you want to deliberately in your code check whether the function was successful or not. And if it was successful, then do something, and if it failed, then do something else. Then you'll store the resultant integer. But on those particular ones, you might actually just want to bypass that and just simply run the function. And that's okay. But on other things like normalize, it's pointless unless you store the result, because why else are you normalizing if not to get the normalized vector? Okay. So that's returning. Then I want to talk about types. Okay. So if we switch over to absolute over here, so the ABS vex function, right? And if you remember from our H script, what absolute is doing is basically returning just a value that is positive. So if it used to be -1, it will now be 1. If it was 1, it will still be 1. It's essentially just dropping the negative sign, but what it's doing is actually calculating the length of that vector. But even if it's an integer or a float, it is essentially a one-dimensional vector. Okay, like if you imagine a number line 0, 1, 2, 3, 4, then the number 4 is 4 units away from the 0. But so is -4. -4 is 4 units away from 0. That's what absolute is actually doing. So if we look at this, right, you can see that there's actually 3 functions here. If we feed it an integer in the absolute function, it's going to return an integer. If we feed it a float, it's going to return a float, and if we feed it a vector, it's going to return a vector. Okay, so it's not just saying that we can feed it anything we want and then get anything we want out of it, because you can't feed it an integer and get a float out. That's why this is written this way, and this is called an overloaded function, where it actually has multiple modes that this is going to run, and it's doing different things inside of each one depending on what you feed it, right? So this function is actually defined 3 times, and it chooses which one of those 3 to actually run, like in the background, what this expression is actually doing, based on what you feed it, and then it will return something different. Okay, so we're going to go more in depth into overloaded functions later, and in fact in future lessons we're going to write our own functions, and therefore we're going to learn how to overload our own functions. But in this particular case, reading this help file, you can see, okay, if I feed it an integer, I'm going to get an integer out. If I feed it a float, I'm going to get a float out. Okay, so now that's typecasting the actual functions and the arguments, but I also want to talk about certain functions. So if you come to xyz_dist, we're going to talk about it here. Certain functions have, instead of typecasting for the overloaded functions, they have a different number of arguments, or maybe a different order of arguments, or different types of each argument. So if you come to the xyz_dist, this is the perfect example of an overloaded function. Okay, they're all returning a float. They're all the same function, xyz_dist, but this mode, you just feed it geometry and a vector, like an origin vector. Okay, you feed it 2 bits of information, and it is going to get you the distance from the origin to the closest point on the geometry, right? So even this one mode of the function has a different explanation of what it does to this one. Then in here, if we feed it the same thing, geometry and an origin, but also give it a primitive and a UV, so an integer for a primitive and a vector for UV, it's going to run an entirely different function. Okay, it's going to do something different to what this is doing, and it explains here exactly what it's doing. Okay, and in the same way, we can feed it a max_dist. So then this will then run a similar function, but with additional, functionality, right? So it's optional whether we include this max_dist or not, right? Whereas it is not optional to include the geometry. Okay, the origin is optional because we need it for any of these, but this one over here does not need an origin. But when it doesn't have an origin, we have to give it a string to a primitive group. Okay. Oh wait, sorry. There is actually the origin. So I guess that's not optional. But you see, the order has changed. So you need to be very careful. Actually, you see here we do have the origin and we do have the geometry, but now there's something inserted in between. Okay, which is exactly why I say this help file, you want to keep it up. You want to keep it open, because you're going to struggle. And often in these wrangle nodes, as you're typing the function, it doesn't pop up with that little help file. It seems to work okay with doing HScript expressions and parameters. The help file often pops up when you open the brackets, but Vex just really doesn't. So open this. Now, I want to talk about this this ampersand sign. Okay. Again, this is one of those hidden bits of information. I mean, it's right there, but if you don't know what this does, you're never going to get this function to do what you're expecting it to do. Okay. When you see this AND sign, the ampersand, it means that this function is going to store information in this variable. So it is not expecting you to pass it information that it will use to perform the function. Instead, what it is asking you to do is pass it the name of an integer where it will store the primitive number. Even in the explanation, it says that it also outputs the primitive number, so that's that, and the UV coordinates for the closest point, right? So primitive and UV. In this here, you can see that the max_dist does not have an ampersand, so this is asking for additional information that we can set or not. It is optional, but this is a value that we're giving it. This is a value we're giving it. This is a value we're giving it. But these two are empty values that it's going to store. Obviously, if we feed it something that's not empty, it's going to overwrite that. Okay, so if we run this function, you would point to some geometry, you'd give it an origin vector from which to measure the distance. Okay, and then you'd actually initialize a primitive. So you'd say in here something like, so it's got to be an integer, and then it would be called prim. And you don't have to initialize it. You don't have to actually give it like a default value, because we're going to be overwriting it using this function. And then a vector uv as well. So in here we would say vector uv, or you could maybe call it my uv or something, just so that you don't confuse yourself. But actually you initialize these two but without defaults, and then you would run this xyz dist function, and then you would feed it maybe a 0 for the geometry, so you're wanting to look in 0, and then you feed it an origin, which is a vector, which, remember, you can use variable or local variables for that, or attributes, so v at p. So then each point is going to actually run this function from a different point position, although this would have to be set to points in order to do that. And then here, instead of feeding it a number, feeding it a value, we're referencing, you just reference your prim and your myuv attribute that you, variables that you've created over here, and it's going to store information in those two. Okay, and then we can leave out that max dist if we don't want to do it. Okay, so this has now run that function. We've given it information to determine how the function is going to react, and then it's actually stored information in here. But at the same time, it is also returning a float. So it's giving us 3 pieces of information, really. So the float that it's giving us is going to be the distance. So you see here it says returns. So it returns the distance to the closest point on the geometry. So we might over here want to say something like f at dist equals, and then it's going to find the distance to that geometry. Now the reason it's coming up with all zeros is because we're feeding it our own piece of geometry, and obviously for each point, the closest point to point 0 is itself. So the distance is 0. So we're not really using this function correctly over here. We will actually be using this in future lessons. A very, very powerful function. For now, I'm just showing as an example. So the reason dist is 0 is because it's finding itself, but still very, very useful to know. And then 0 over here, this is saying grab my first input. This we're feeding at the point position, so each point knows where to measure the distance from. And then this prim and prim uv have actually had data written to it. Now obviously if we feed it a variable like this, we can't see this data, but we can write it out. So we can say I at prim, or we can call it whatever we want, okay, but it's just easier to export it with the same name, and then equals prim. And so you'll see here now this is a list of the primitive number that each one of these points is finding. Okay, and then if we write out v at myuv equals myuv, then we're going to see the UVs as well. So then it's got the UV coordinate and the primitive number of where the closest point on from this point is on this piece of geometry that we've referenced, which is obviously itself. So kind of, you know, in this context doesn't really matter, but normally you'd feed this as a 1 and you'd feed it another piece of geometry. Okay. So very important for you to understand what this ampersand sign says, and then how to read all the different arguments and choose which mode you want. You know, do we need the primitive and UV data? If you don't need that, you just need the distance, then use this first mode. Do we need to feed it a primitive group or not, because that's all this is doing. You can see here that this is exactly the same function as that, but it includes a prim group, and it's these two are the same as these two, but it includes the prim group. So do we need the prim group or not? If we do, then we need to write it this way and insert that prim group over here. Okay. Now also you'll find in these help files that at the bottom, sometimes it is hidden, so that there is this show or hide arguments. Normally they are shown by default and you have to hide them, but in this example, for example, the point, they actually are hidden by default. So just keep that in mind. Maybe click it, and unfortunately it doesn't show whether it's shown or hidden. It's just, it's a bit annoying. So just click it and see what appears and disappears. And this here will actually give you a little bit of an explanation of what each of those arguments is doing. Including here, you'll see it overwrites this variable with the number of the closest primitive. So that's it doing exactly what we said. Right. And then it tells you what this function returns. Okay. So this is how you would use and read the help file to figure out your different overloaded functions, all the options you have, what arguments it needs, the order to put them in, the types to cast them as, and what is getting returned out of the function. Plus, obviously, what the function is doing itself. One thing to point out, though, and the reason why I popped this reading attributes one open, is just that sometimes functions are just multiple types within one function. So when I search for the point function or the primitive function, when you do open it up, you'll see that it is actually just a subtype of the reading attributes function. And then it's worth reading through all of them to kind of see how they each act on the different classes. Reading a detail attribute and a prim attribute is very similar. It's just that there's certain arguments that are not quite the same. So obviously read point, but you can actually see what's different from point to prim. And it'll do the same here. It's going to show you exactly what it returns and all the different arguments it needs, and there's even two different types. So in this case, it actually takes the same arguments, but what determines the difference between these two is the type that it returns. So if you don't cast the attribute where you're storing this, it doesn't know which of these two to select from, and that is why I said it is so vital to cast. So if you're going to run the point function, if I'm saying f at my attrib equals point, and then I fill in that point function, then I'm going to be running this one because I've said f at, right? Because it is not an array. If I want, so this square bracket references an array. We are going to talk more about arrays in the future, so don't worry about this too much for now, but just so you know, whenever you see the square brackets, it means that this is an array. So f, and then I run this, is going to be grabbing a float. You'll see here it says type, which means that this can actually take any type, float, integer, string, it depends on the type of the actual attribute, and it'll explain that in here. But if I say f array at my attribute, then it means that it's going to be running the second mode of this function. And although it looks the same, it looks like it's taking the same arguments, inside it's actually doing a few different things. Fetching the point attribute of an array is different to fetching just a static value. Okay, so very important to understand how that all works. One more thing I just want to point out, which I see here in the detail function, is at the end here it says ignored equals 0. Now, whenever you see it says equals something, what that is telling you is that it has a default value. So if you do not fill this value in, if you feed it just two arguments, geometry and a string for the attribute name, it will still work. It will function, and it will function as though you gave the value 0 to this argument. Okay, so if you fill it in with 3 arguments and the last one is 0, it's the same as filling it in with just 2 arguments. But if you want to override this value, then you feed it a third argument, which could be then 1 instead of 0. And then you tell it whether it should be ignored or not. And it'll explain what this does. Okay. Now this is a little bit different. Having a default value is different to having optional values here, like with max dist included or not. Because max dist does not have a default. If it is left out, it does not default to a value. It changes the method in which it actually runs this XYZ dist. So the coding that's happening in the background inside of this function, the stuff that's running that you don't see, is different from this version to this version. In this version, it is limiting itself to a max dist. In this version, it is not limiting itself to any maximum distance. So the way that it operates is different. In fact, you might even find that these run at different computational speeds, because without having to run a max dist function, this is probably heavier than here, where it limits itself to a certain distance and only has to scan up to that distance and then it stops. So this function will be more efficient. And the max dist value is not just set to a default of infinite in this function. Instead, the insides are actually functioning differently. Okay? Whereas in this case, when you leave it out, it is as though you gave it the value of 0. Okay. Right. So I just thought I'll point that out. I hope that does make sense, but it will make sense the more we move forward and actually start to use these functions. All right. So rely on the help file. It is full of very valuable information. It really does explain how to use each function, and above and beyond just how to read this section and the list of arguments, it also gives you a lot of good examples normally, or even scene files where they've used that particular function, and it shows you how to use it. There's different, there's other related functions. So there's so much in here, you almost shouldn't get lost. Okay, I mean, even look at this reading attributes one, and not only does it explain all the different types of reading attributes, it then goes into checking other things, giving you examples. It's fantastic. Okay, so they've really put in a lot of effort into making these help files help you, So this is your dictionary. We now know, we've spoken about the syntax. So in the next lesson, we're going to start doing some actual coding. We're going to do some examples using both the syntax that we've used and then these help cards, and build up a few expressions and start writing some chunks of useful code. Okay, so thank you very much for listening, everyone, and I look forward to seeing you in the next lesson.